I hope to our dear friends in Unizik, you had a successful GST examination. That's your GS examination, because I am aware that you friends started taking that exam, that course, from Monday. I want to believe that you are done with the exam. That's your GS exam. I also want to believe that you did your best while looking forward to your ace splashes. All right. So I've been keeping it low, waiting for you to be done with your GS examination so that we can still continue with our, light review classes on physics, knowing that you friends will be taking on physics, I think, on Saturday. So once again, I say welcome to join the class. So in this live class, we are going to be summarizing something quickly on, the concept of electromagnetic field. Yes, electromagnetic field, where you talk about the joint interaction between electric field and magnetic field. So in this class, what we wish to achieve is to deal with Maxwell's equations. Okay, Maxwell's equations. Good evening, Paul Ugochukwu Ofomejulu. You're welcome to join the class. Please, just once you join the class, share the link to your friends so that they can also connect to the live class. Let's remind ourselves of some important things, okay, in this aspect. Now we have part 2 of this revision, because I've already put you through part 1, electrostatics and current electricity, or simply put, we talk about electricity. We are done with that part, and I want to believe that you have been able to access the playlists where the video lessons, okay, covering everything you need to know about electricity, were kept for you. So in the same way, in part 2, we're going to look at the concept of magnetic field and electromagnetic induction. So just like you saw on the board, we will be giving attention to Maxwell's equations, okay? Yeah, that's really one of the things that this class is based on. After which, we are also going to talk about the concept of the magnitude of magnetic induction at a point, a given distance away from a charge or a conductor. Now, basic aspect of magnetic field is something I want to believe that we are aware of that already. Sorry, sir, did you do a video on wave? I am having issues with wave. Yes, in part 3, the playlist already covers lessons, all right, on waves. They are there on this channel. So what I'm just trying to do with this live class is just to open your eyes to certain key concepts as well too, per the area of focus in the course. Now, when you're dealing with, magnetic field, when you're dealing with electric field, there are concepts you meet. For example, you talk about charge, you talk about current in electric field. you talk about electric field intensity or electric field strength, which is also simply referred to as electric field. That's under electrostatics, okay? And then you could also remember that in part one, all right, in part one, we talk about the concept of current density. Current density, and we also have the concept of charge density, which has to do with the quantity of charge occupying a given area. Now, when you go to magnetic field, you meet the concept of, magnetic field strength, also known as magnetic induction. We use capital letter B for it. Okay, magnetic induction, capital letter B. You can see that on the board. Some of the quantities I have mentioned. Okay, I also remember in electrostatics, we dealt with the concept of Gauss law. Gauss law. In that part one playlist, where the video lessons, just some video lessons that I extracted, which are core areas of your exam questions. All right, in that part one, you have all these concepts, Gauss law, talk about Coulomb's law. Okay, yeah. Now, if you move on to magnetic field, you study the concept of magnetic flux density, also known as magnetic field strength. Okay, I think we also call it magnetic induction also, if you so wish. We use the symbol capital letter B for it. Okay, we use the symbol capital letter B. And that quantity is very important because it determines the strength of the field. So what Maxwell's equation tends to do now is bring in the concept of electrostatics, bring in the concept of magnetic field, put these two fields together to create what is called electromagnetic field. So there are certain equations that we meet there, which your examiners will also be interested in your knowing. Okay, they've always asked questions related to that also. And so it's important that we talk about this Maxwell's equation. All right, there is nothing much there if they're asking you questions on it. It's just for you to know each of the equation, the law that they define under electromagnetic field, all right, the law that they represent, just for you to know it. That's it. You're not solving any question on it. Look at the equation still. You're not solving any question. No calculation is usually given for students to deal with, okay? Because you are not meant to be exposed to, well, I wouldn't say that you're not meant to, but let's say your outline, course outline, does not cover some of the symbols you saw there. Like you see something like V bar, which we call the nabla or the del operator, the del operator. It is an operator that is met under vector calculus, where you carry out, a second derivative or so. So what your examiner just wanted to know is memorize this Maxwell's equation. Are you following, right? Then know which law each of them represents. So first of all, what are these? What are the Maxwell's equation? What are they? So Maxwell's equations are simply a set of four equations that are used to describe the fundamental concept of electromagnetism. All right? They are used to describe the fundamental concept or laws of electromagnetism. That is what these Maxwell's equations are. Like I said, they are a set of what? Set of four equations that describe the fundamental concept or laws of electromagnetism. You can see those equations on the board, the four of them. So you could copy them, and if you're not aware of it, you memorize them. Very important. Like I said, some of you might be exposed to the questions on it. These equations you have there on the board are the differential form. They are the differential form or the point form of Maxwell's equation. Those equations, the four of them, they are the differential form or the point form of Maxwell's equation. You see, with this equation, it helps us, or the equations help us to understand the concept of radio waves, all right, the concept of electromagnetism. If you want to learn much or go deeper into this aspect of wave study, these equations are very, very important. So quickly, the first equation, we want to know what law it defines. The second equation, the third, and the fourth equation. We want to know the law that they describe or they represent. And then, of course, the meaning of the quantities there. Your examiner wants you to know the meaning of the quantities. So you follow along as I explain this concept. I'm going to display the board, all right, and then we analyze it. Remember, I told you something for this semester. Stress is going to be much more reduced because much of all these works I've done them already, okay? But don't forget, like I said, the equation displayed on the board is the differential form of Maxwell's equation. We also have the integral form. On this channel, if you come to the homepage of GMAT 41, this channel, click on Visit Community. Click on Visit Community. It will take you to the channels community. On the channels community, click on New. Click on New. So it will bring out the updates that I've already posted. Just this evening, I posted, the integral form together with the differential form of Maxwell's equation. Because the examiner can also test you on the area where you are given the differential form. And then they're asking you what is the integral form of that equation. So please, at the end of this live class, quickly click on Visit Community on this channel. I've always advised people to make use of that community because usually I give updates there. Then if you go to that community, click on New or Newest, yeah, something like that, Newest. So you can see the latest update, which focuses on the integral form of Maxwell's equation. Like I said, what I'm about to display on the board is the differential form. So let us go to the board and see what we have. Let us go to the board and see what we have. So the first equation there, you have that first equation, we have something that looks like V bar, all right? Something that looks like what? V bar. What does it represent? Like I said, it is called a del operator. It is called what? A del operator. You don't need to stress yourself on it. This is what I mean. Look at this quantity. Is it quantity or operator? This is a del operator. We also call it nabla. It's actually used to represent usually the second derivative of something. Yeah, with respect to another. Usually if I give it with respect to time, I have something like this. Or if maybe I say with respect to x, depending. Okay, so second derivative, second partial derivative of a given function. Like in this case, the function is electric field intensity. Okay, so this V bar, like I said, is just an operator. We call it a del operator, a differential operator. Okay, so for those of you that are going to do vector calculus in your higher level, you will meet that concept. Okay, now this point you're seeing here, that point represents divergence. That point represents what? Divergence. Look at it. So this thing simply means intensity. Good. The divergence of this vector is equal to the charge density. This row you are seeing there it seems the network just cut off, the ongoing class. That's quite sad. That's a challenge we have sometimes, and like I've always advised you friends, please make sure that you always make use of a pre-recorded, uploaded video. You can see the network might just be bad due to the weather. We are in rainy season now. It's not like last semester, which was dry season. We had some good network sometimes. All right. I was explaining the concept of, Maxwell's equation, such that some of the things I wrote on the board, because from what I am observing here, it cut off even before I explained some of those things. But all the same, I think the network is back now. So let's see. Let's see. All right. So quickly, I'm going to be a bit fast. I've actually explained this first guy, but it appears that, the network cut it off. It appears the network cut it off. So I explained that this is a del operator called nabla symbol. Now it is operating on this vector quantity. This vector quantity is electric field strength or electric field intensity or simply electric field. These points here represent divergence. Divergence is a mathematical symbol, right? Or a mathematical process. It's a mathematical process. So we have this to be the divergence of the electric field intensity is equal to the charge density. The charge density divided by permittivity of free space. And I went further to explain that this first Maxwell's equation, well, there is nothing like first Maxwell's equation, second Maxwell, or third Maxwell. What do I mean by that? This equation does not mean that this is number 1, compulsory number 2, number 3. No, they are not numbered. Any one that comes to your mind, that's okay. Is that okay? So this first one we have here, this is number 1, this first one. This formula or this equation rather can still be written in this form. Can be written in this form, where we have this to be the divergence of this quantity. The divergence of this quantity, which, of course, this D you're seeing here is obtained from multiplying this electric field intensity by permittivity of free space. Let me indicate it. Let me indicate that D is equal to electric field intensity times what? Permittivity of free space. Usually we add the polarity of the electric field plus electric field polarity, but we don't consider that polarity much when dealing with this equation. For that reason, the polarity P, I just decided not to show it. Is that okay? I decided not to show it. So you want to remember that this D here is equal to this product so that you still get this equation. So it's either you see the equation in this form or you see it in this form. Does that make sense, right? Good. This will now take us to the second one. However, you want to take note of the name of this equation. This equation is called Gauss' law. Gauss' law of electricity. Gauss' law of electricity. Okay? All right. The next is this second one. And this second equation we have here, equation number 2 we have here, is telling us that the divergence of the magnetic field strength, otherwise known as magnetic flux density, the divergence of this magnetic flux density is equal to 0. The divergence of that magnetic flux density is equal to what? 0. That Maxwell's equation is called Gauss' law of magnetism. Gauss' law of magnetism. And what is the implication of this particular law? What is the implication of this particular law? Gauss' law of magnetism simply implies that there is no existence of magnetic monopole. Magnetic monopole does not exist. So in the other way around, we can say non-existence of magnetic monopole, which simply means that a magnet cannot have just one pole. In a magnetic field, you must have two poles, the north and the south pole. That is the implication of this guy. It's important you take note of it. Because in the study of electric field on its own and magnetic field on its own, we don't meet this. We don't meet this. So now that we've talked about this, under Maxwell's equation, you want to know the implication. This one is Gauss' law. We met it under electrostatics. In part 1 of this Phys 102 revision, you have a video lesson that covers that Gauss' law. So you meet an equation that is close to this, where of course the Gauss' law tells us that the electric flux is equal to the charge enclosed divided by the permittivity of free space. Now, this symbol you are seeing is called the charge density. This is permittivity of free space. I've defined this as electric field. And I told you that this is also a concept of charge density because it is obtained from the product of these two guys. I've told you the implication of this Maxwell's equation. Non-existence of magnetic monopole. Simply put, because that's just a grammar, non-existence of magnetic monopole. What that simply means is this equation is telling us that a magnet can never have one pole. In a magnetic field, you don't talk about just one pole. There will always be two poles. So in magnetic field, or a magnet simply is dipole in nature. So sometimes the examiner can just ask you this: what's the implication, or which of the following Maxwell's equation expresses magnetic non-existence of magnetic monopole? The correct answer is this equation. And we refer to this equation as Maxwell's equation. This Maxwell's equation, we refer to it as Gauss' law of magnetism. Gauss' law of magnetism. Please, let's move on quickly. I think network don't understand what network is doing, so let's just be a bit fast. Like I said, you're not calculating anything on this because you're not doing any second order derivative in this case. No, your examiner just wants you to memorize this equation, know the law they represent, and know the meaning of the quantities, and then the implication of any one of them when necessary. The implication of Gauss' law, you have it in that part 1. If you go to the playlist, all right, become a channel member, you access that playlist, you see the implication. I've already stated Gauss' law, so from there you can actually get the implication. Of course, there are 5 main implications of Gauss' law, which you meet there in that playlist under the video lesson that covers Gauss' law. I've already created this exam focus playlist for you, just trying to summarize certain key things. This Maxwell's equation, I just want to talk about the meaning of the quantities and what the equations represent in terms of the law they define. Let's go to number 3 quickly, no time. This number 3, you now notice that we are no longer talking about divergence. This point represents divergence in this case. We are not talking about this cross here. This cross represents curl of a vector function. Curl. So those that are going to deal with the vector calculus in their higher level, are you getting me? Vector calculus. Of course, addressing 100 level students, let us not say in your 200 level, those that will study, there is a course you study called vector calculus. Some of you will meet this concept of Nabla's symbol, right? Which is a del operator, where it operates with respect to talking about the mathematical process called divergence. We use dot, and then curl. We use this cross. So in this case of number 3, the Maxwell's equation is telling us that the curl of this vector valued function, this vector function, which of course is the electric field, curl of the electric field is equal to negative the partial rate of change of magnetic flux density. The partial rate of change of magnetic flux density, or simply put, negative the partial derivative of the magnetic flux density or magnetic field strength, because this B is also the strength of the magnetic field with respect to what? Time. So that is what this equation is. And if you crack your brain, you will agree with me that under electromagnetic induction, of course, I've dealt with that already, and in the playlist part 2, where I arranged exam focused video lesson that will guide you 100%, yes. You have the video lesson that deals with electromagnetic induction, where you stated, the Michael Faraday's law of electromagnetic induction. You stated the Lenz's law of electromagnetic induction, And then I remember that from the concept of Faraday's law of electromagnetic induction, the second law, to be specific, you move further and then you bring in the concept of Newman's equation. That Newman's equation is something that looks like this. It's something that looks like this. As a matter of fact, in the short section of this channel, I had actually dropped a question and asked people to solve it and get the rate of change of flux. Are you following, right? So why am I actually talking about this concept? This is to remind you that this is something you've met. Remember, I told you from the beginning that Maxwell's equation is simply a collection of formulas that you met under electricity, electrostatics, and current electricity, plus formulas you meet under magnetic field. The interaction of, current and charge to produce magnetic field and electromagnetic induction. The interaction of charges and current to produce magnetism, which of course we refer to as electromagnetic field. The collection of these quantities together from these two fields makes up these things that are called Maxwell's equation. Maxwell came up with those equations. And so that is it. These are things you've actually met in one way or the other. It's just that in this case now we are writing them much with respect to differentiation symbol, partial differentiation symbol. Like I said, we have the integral form of this equation. Take note, I've told you how to find it out, okay? Go through this channel community. Please let us move on. This equation is Faraday's equation. Faraday's law. Faraday's law. Faraday's law. This Maxwell's equation represents Faraday's law of electromagnetic induction. That takes us to this last one. That takes us to this last one. All right. So this last one, this Maxwell's equation is telling us that the curl of this H. This H is actually called magnetic. It's a magnetic concept, all right? This H. Magnetic flux, magnetic field intensity or flux density. It is quite related to this B. It is related to this B through what we call the magnetic permeability. H is equal to, think of this concept. Yeah. And we know that this magnetic permeability is a constant. Is what? A constant. So that H is still a concept of magnetic flux density. Are you following? But it has a special name given to it. And you want to take note of that concept. You want to take note of what that H specifically is. So the magnetic field intensity. Magnetic what? Field intensity. It's related to this. It's just that this one, you see this B, I had called it magnetic field intensity earlier. Yes, I'm not wrong, because it defines the strength of a magnetic field. And like I said rightly, this H and this B, they are almost similar. The only difference is that there is this constant linking both of them, which is the magnetic permeability. This guy is a constant, just like you have this. That's this permittivity of free space under electric field. This one is magnetic permeability constant. Simply permeability of free space. Yeah, under magnetic field, you meet it in this channel, right? You meet it, so it's nothing new. It has a value 4 pi times 10 to the power of minus 7 Henry per meter. So this is magnetic field intensity, this H. Let's go back to this equation. The curl of the magnetic field intensity is equal to the current density. This J represents what? Current density. Now, this current density, we have met it before, right? In part 1 of the exam focus playlist created specifically for your exam, in part 1, which focuses on electrostatics and current electricity. Just the introductory part of current electricity, where we talked about the concept of resistivity. Concept of what? Resistivity. As a matter of fact, resistivity was derived from the application of current density and electric field intensity. Current density is J and electric field intensity is E. The ratio of current density divided by electric field intensity, that is J over E, gives us our resistivity. So why am I highlighting on this? This quantity, you know it. If you've taken the lesson on, the concept of resistivity of a material, you should meet this, because we use this quantity also to derive the resistivity of a material. So the curl of the magnetic field intensity is equal to the current density plus the partial derivative, or the rate of change of charge density with respect to time. Rate of change of what? Charge density, or partial derivative of this charge density divided by what? The partial derivative, that is over the partial derivative with respect to time. Just like you have dy dx. This one is partial derivative of this charge density with respect to what? With respect to time. So you want to take note of these equations here. And what does this particular equation, which law does it define? This equation defines the Ampere-Maxwell equation. Ampere-Maxwell equation. And no wonder under magnetic field, electromagnetic induction, we have that law we call the Ampere-Circuital law. The Ampere-Circuital law, which is the magnetic equivalent. Ampere-Circuital law is met under magnetic field. It is the magnetic equivalent of Gauss' law in electric field. So when we talk about Gauss' law in electric field, in magnetic field, we talk about Ampere-Circuital law. A quick one, let me just remind you of the meaning of some of these quantities that we've mentioned. Especially, I want to write the meaning of this quantity, this D, because it's new to us. This one is not so new, but I'm still going to write it, okay, because of the symbol that was used there. I hope the network is still intact. Let me check. Okay, still intact. As we round off, this row represents charge density. Charge density, the quantity of charge per unit area. Okay, then D, electric flux density. D is electric flux density. D, electric flux density. Is there any other quantity? Okay, H, magnetic field intensity. Magnetic field intensity. That's the specific name of this particular quantity. B is sometimes called magnetic, flux density. B, magnetic flux density, magnetic induction. Though sometimes I also even refer to it as magnetic field strength, because it defines the strength of the magnetic field. But this particular quantity H is really what we call magnetic field strength. I've already told you the relationship between H and B, so you want to take note of that. In conclusion, I want you to remember this. Under magnetic field, we have this law we call the Biot-Savart law. Biot-Savart law tells us that the magnitude of the magnetic induction B is directly proportional to the product of the charge and the velocity component, and inversely proportional to the square of the distance between the charge and the field. There's another alternative way of stating it, where we bring in, the concept of the differential length And then we state Biot-Savart law alternatively as the magnitude of the magnetic induction is directly proportional to the product of the charge and the differential element of length, and inversely proportional to the square of the distance, magnetic equivalence of Coulomb's law under electrostatics. So in magnetic field, we talk about Biot-Savart law. The equivalent of that guy in electric field is Coulomb's law. If you check their statements, you see this corollary, this relationship. Then I had also mentioned Gauss' law. And here I told you Ampere-Maxwell equation. We have a law we call the Ampere-Secutor law. The Ampere-Secutor conductor is equal to the product of the magnetic permeability and current. This equation you're seeing here is called the Ampere-Secutor law. It's called the what? Ampere-Secutor law. Ampere-Secutor law. That Ampere-Secutor law in magnetic field is equivalent to Gauss' law in electric field. So that is that. We are done with this concept. Okay, we are done with this concept, and you want to take note of it. I've been able to, analyze this concept of Maxwell's equation. So what other parts do you want to give attention to in this magnetic field and electromagnetic? The network keeps hanging and all right. So take note of those formulas I asked you to remember. You need them as you're preparing for your examination. The network is just messing up. Please look at this Maxwell's equation. That's good. I'm going to wipe them from the board. I'm going to wipe them from the board now. And the network continues to want to frustrate, but we are not going to give in. Let's just quickly round off what I want us to deal with. We are talking about the magnitude of the magnetic flux density, of the magnetic induction for different charge configuration. The first one, if you're given a problem on infinite long wire and you're asked to determine the magnetic flux density, you're asked to determine the magnetic induction, which formula do you use? This is the formula you use. B is equal to magnetic permeability constant, or simply magnetic constant, times current divided by 2 pi A, where A is the distance of the charge, the distance of the wire in this case, because the wire is acting as a charge in this case, from the field position. Then we want to look at the magnetic induction at the center of a coil, at the center of a coil, The formula of the magnetic induction, you want to take note of it. There we have the magnetic induction to be equal to the magnetic permeability times current times this capital letter N is number of turns of wire, number of turns, divided by 2R, divided by 2R. Take note of that. This N over R, if R is the length of that maybe charge configuration, N over R can be replaced with small letter n, where that small letter n we refer to it as the number of turns per unit length. So you want to take note of that concept. This will take us to the third one. Inside a solenoid, inside a solenoid, inside a solenoid, what is the magnetic induction? Inside the solenoid, the magnetic induction B is going to be this quantity. Is going to be equal to the magnetic permeability times current, then times small letter n, where small letter n is equal to the number of turns per unit length. L is the length. L is the length. And I want to tell you something. If maybe you have a circular, charge configuration, something like this, I hope the network hasn't cut me off. Let's see. All right. If you have a charge configuration that is circular, for example, take note. This circle is the perimeter, the circumference, the length of a circle. Just like you have this 2 pi a. If I cut this rubber band, it's circular like this. If I cut it, it will become straight line. So now give you a length. So if you're dealing with this small letter n, number of turns per unit length, you know that if you have a coil, usually coil that you see in your electrical appliances, it's there in fan, in other electrical appliances, you have number of turns of wire around it. If you take the video lesson on that, we are introduced the concept of this, magnetic induction for different charge configuration. You would see display diagram of coils and solenoid. So the number of turns per unit length along the length of this coil. So they could give it to you as maybe the circumference of that charge configuration. So the number of turns per unit length is what we represented with this small letter n. So you take note of that quantity. Then finally, number 4, at one end of a solenoid. At one end of a solenoid, we have the magnetic induction to be equal to magnetic permeability times current, then times n over 2. And don't forget that this small letter n, once again, is capital letter N divided by L. So this could still be written as magnetic permeability times current times number of turns all over 2L. If you look at this formula and look at this formula, they are similar. They are what? Similar. Yeah. The only difference is that this R here represents the radius of the circular coil in this case. Whereas if you come here, this L here is actually the length of the solenoid. A solenoid is just like a cylindrical coil, a cylindrical object over which you coiled tons of wire. So if you pull out that tons of wire turned, you're going to have something of this form. You observe that, right? That gives us our solenoid. So there is a length. That's what this represents. It's all right. So those formulas are important for you to take note of, please. Take note of them. They're important. So the formulas you have here are those that you need to know for different charge configuration in calculating the magnetic induction. It's all right. So once again, take note of the formula you have there on the board. Very important. So as we conclude this live class, I want to draw your attention to the introductory part of magnetic field. All right, we're talking about the force on a charge introduced into magnetic field. You have F equal to QVB sin theta. Remember this formula. You have another force formula in terms of a current carrying conductor of length L. The force, in that case, is BIL sin theta. Remember, then to calculate the induced EMF, you have several formulas for it. Induced EMF, the magnitude can be the rate of change of flux. All right, and you can also have the concept of the magnitude of induced EMF, which is BLV sin theta. BLV sin theta. You want to take note of that. You want to also take note of the force between two parallel current carrying conductor. All right, you want to take note of that. Then your electromagnetic induction, the laws of electromagnetic induction, take note of them. I've mentioned them already. Faraday's law, Lenz's law, all right? Now under Faraday, it extends to Newman. You want to take note of that. And think, basically, those are the things you want to be well prepared for. They are calculations, okay? Calculations are already covered on this channel, and I've created a playlist to guide you in them. So with this, we are done with the concept of magnetic field and electromagnetic induction. So I wish you well in this part 2 in case your exam questions come from this part. Tomorrow, by God's willing, we will be concluding the revision on Physics 102. We'll be looking at part 3, where we'll cover wave, right? Then refraction and reflection of light. However, remember that you have the playlist already created for you. So you make use of the playlist and of course enjoy your studies. Remember, like I said, make use of your textbook. The worked examples in your textbooks, make use of them. Then, of course, make sure you solve all the questions that you have there. Very important. Make sure you solve all the questions you have there. And the channel here, this channel, GMAETS 41's channel, will guide you in this aspect. In case you have any challenge, make use of the playlists of this channel that I've created for you for this Physics 102 exam revision. Don't forget, physics is a course where if you're going for an examination on it, you cannot predict how the question is going to be. So you want to be well prepared, right? You want to be well prepared. And I have done my part to assist you guys. Once again, like I stated in part 1, when I was giving a quick summary of it, avoid your chat GPT now or any AI platform. Avoid them now. Are you following? Focus on your lecture notes, focus on your textbook, the solved examples in your textbooks and some of the exercises. Yes. Focus on this channel, right? This revision, the areas I'm pointing to, and then the 3 playlists I created for exam revision on Physics 107. Focus on that. These are the things that will help you go in there on Saturday. And I tell you, you will blast your A's. A splashes with nothing stopping it. Yes, nothing. So be confident. Make sure you are doing your revision as I've guided you. And you have excellence awaiting you. Take care of yourself. Do enjoy your night rest. I'll be seeing you hopefully tomorrow as we conclude with wave, refraction, and reflection. Remember, follow up with their calculations. The playlist will guide you, okay? Nothing is there in the calculation. You have your textbook where you can consult questions from, or you have this channel, all right? All the video lessons, your calculations that are exam related, they are there in the playlist. Once again, I created specifically for this revision. You have part 1, you have part 2, you have part 3. Some of your exam questions might even come from the worked examples in the lecture videos. Are you following, as we have on this channel? But much more, I am pretty sure, are you getting me, from your textbook, those worked examples. Yes, don't joke with them. Those worked examples, those things that sometimes they will list point for you, maybe the properties of this, all right, the laws of that, those things, these are areas that your exam questions will come from. ChatGPT is not going to give you any question that are actually the target of maybe what your examiner wants of you. All right, Chidera will be what time tomorrow, please? All right, it's going to be earlier than this time. Let's say plus minus by 5 p.m., God's willing. By 5 p.m., I will deliver that last exam focus revision. 5 p.m. tomorrow. All right, guys, good night.